Light emitting diode. So here we are going to see about the optical sources like LED and laser, how it works and which one is efficient, and we'll see the comparison of both LED and laser. So optical sources, it plays an important role in the fiber optic communication. It is used to convert the electrical energy into optical energy. Hence it is coming under the transducer. Okay, transducer is nothing but it converts one form of energy into another form. Basically we have two types of optical sources that are present in the optical communication. One is the LED, the other one is the laser. It is otherwise called as injection laser diode. So we should have two important conditions to be satisfied. The first one is the source power must be coupled into the fiber with minimum coupling loss. Second one, the power transferred from the fiber to detector should have maximum coupling efficiency. Next, we'll see the few requirements of light sources. The light that is coming out of the source should be highly directional, and the light emitted from the light source should be operated at the desired wavelengths of the optical fiber communication, like 1.3 micrometer or 1.55 micrometer. And then we need to couple large amount of power, hence the emitting area should be very small, and for the operation of light source it should require very small amount of power for its operation. And here we can see the output optical power can be directly modulated by simply varying the input current, and irrespective of the temperature changes the optical output should remain stable, and the light source must be compact in size and high efficiency, and we need high optical power and also high coupling efficiency, and the light that is coming out of the source should have very narrow spectral width in order to minimize the dispersion effect. And the last point, the source should be cheap. And here if you compare LED and laser, we know LED is a monochromatic incoherent source. Okay, whereas laser, light amplification by stimulated emission of radiation, it is a monochromatic only, but it is a coherent source. It's providing a more directional beam coming out of the light source. So optical source converts electrical energy, that is current, into optical energy in the form of light. So the light emitted by the optical source, whatever it is, LED or ILD, is launched or coupled into the fiber for further transmission. The fiber optic communication performance, the fiber optic data link performance depends on the amount of optical power that is launched into the optical fiber. Here we have two types of band gap materials. They are used to make LED, laser, and then the switches, detectors, etc. Here we have two types of materials, direct band gap material and indirect band gap material. It is defined based on the conduction band and the valence band. Electron transition to takes place to or from the conduction band with absorption, either with the method of absorption or by emission of photon. These are all the two important functions. One is the absorption of photon or emission of photon. The photon can be absorbed or the photon can be emitted. Here the condition is what? The both energy and momentum should be conserved. So first let me see the definition of direct band gap. So direct band gap material, in which we have conduction band and valence band. The electron from the conduction band can recombine with the hole in valence band, and hence after the recombination it emits a photon of energy at h mu. Here in this direct band gap, electron and hole have same momentum value, hence direct recombination is possible, whereas the lifetime of charge carrier is very less. Hence it is used to fabricate LED and ILDs, and it is providing higher internal quantum efficiency. That's all about direct band gap. Going to indirect band gap, so in the conduction band we have less number of electrons, whereas in valence band we have maximum energy level of holes in the valence band. So we can see from this the momentum is not same, it is different in both the levels. So how to do the band to band recombination? So here for the direct combination it is not possible, hence the photon energy or photon momentum is very small. In order to have a recombination of electron and hole, we are in need of third particle called as phonon. Here, the lifetime of charge carrier is more, hence it is used to fabricate rectifier diodes and transistors, amplifiers and switches. Here, this diagram explains the first part shows the direct recombination and the second one shows indirect band gap material. In the first case, we can see the momentum is same. We can see the conduction band and valence band. Direct combination is possible. So after recombination, it emits an energy of h mu. Coming to the second diagram, we can see in the valence band we have more number of holes, whereas in conduction band we can see less number of electrons. So here direct recombination is possible. Hence, it does not have enough momentum. Hence, we are in need of phonon, the third particle, for recombination to takes place. And these are all the important characteristics of LED are high radiance and fast emission response time and high quantum efficiency. So first we'll see the definition of all the three. First one, radiance. It's nothing but measure of optical power radiated into a unit solid angle per unit area of the emitting surface. The unit is watts. And high radiance is required in order to couple the power, high optical power levels into the fiber. Then second one, emission response time. Emission response time is defined as the time delay between the application of a current pulse and the onset of optical emission. At what time the input pulse is given, at what time the according to the input how the system responds. That is the delay between these two is defined as what, emission response time. And the time delay is an important factor which limits the bandwidth of operation. Next one is quantum efficiency. It is defined as fraction of electron hole pairs recombined radiatively.